Now, the previous limit video I did kind of brings us to L'Hopital's rule. L'Hopital's rule says that if I have an indeterminate indeterminate limit, okay, these are the indeterminate forms. The one I'm going to be most focused on in this video is 0 over 0, because that's the one you really need for the AP calculus exam. The other ones are more prevalent in Calc 2 as you're doing series and sequences. And you're certainly useful in Calc 1, but you really only need that 0 over 0. So that's the proof I'm going to look at as well. What L'Hopital's rule says is that if you have an indeterminate form, you have a function divided by another function, the limit will be the same as if you took the derivative of the top and derivative of the bottom. Notice it isn't product rule, it's just, quotient rule, it's just saying take the derivative of the top, take the derivative of the bottom. Okay, let me show you why this works, or how it works, and then we'll look at why. So these are a couple that we looked at in the previous video, and let's check and see if they're indeterminate. So like this first one, 25 minus 40 plus 15, 0 over 0. So L'Hopital's rule says if you get an indeterminate form like 0 over 0, you can take the derivative of the top, which would be 2x plus 8. I'm really doing this shorthand. By rights, you should rewrite it out and say it's the limit as x approaches a of 2x plus 8. The derivative of the bottom is just 1. Plug in 5 again. 2 times 5, negative 5, plus 8 is negative 2. That's the limit. Okay, let's go to this next one. Sine of 0 over 0, right? So it is an indeterminate form. So the derivative of the bottom is easy. That's just 8. Derivative of the top needs a little chain rule. 4 cosine of 4x. We plug in 0 again. We have 4 times 1 over 8. It's just 1/2. Next, plugging in 3, we get 0 over 0. So the derivative of the top is 2x. Derivative of the bottom is 2x minus 10. Plug in 3 again, we get 6 over negative 4. 6 over negative 4 reduces to negative 3/2. So it's really saving us the work on the ones we had to factor. Okay. All right, next one. If I plug in 2, I get 24 minus 8. I get 16 over 3. And I just threw this one in there because you don't need L'Hopital's rule for that. Please be aware. And remember, the L'Hopital's rule works for indeterminate forms. We don't need it for everything. We need it for the ones that needed more work. Okay. All right, I plug in 0. I get 0 over 0. So L'Hopital's rule, 18x squared minus 10x plus 10, or 1. Plug in 0 again, and we get 10. Again, I'm really doing this in a shorthand. If you had to write this out, you would be expected to say, a new limit statement, write the derivative on the top and bottom. In the interest of time, I'm just kind of shorthanding this, and probably at a multiple choice test or something, it's probably how you would do it. As x approaches 2, 5 times 8 over. So what you see here is the answer is 10, and we didn't need L'Hopital's rule. So this first one, you plug in 0, you get 0 over 0. So we use L'Hopital's rule, and we say, okay, it's 12x squared minus 14x over 2x. And you plug in 0, and you get 0 over 0 again. Well, because it's still indeterminate, we can still use L'Hopital's rule. So 24x minus 14 is the derivative. 2 is the derivative. Plug in 0. We get negative 14 over 2, which is negative 7. So we can use L'Hopital again and again as long as it stays indeterminate. Okay. So like this next one, we plug in 0. We get 0 over 0, so we do L'Hopital. We plug in 0, and we get 1 over 0. That is not indeterminate, and therefore we have to stop. But 1 over 0, that means the limit does not exist. Okay, so L'Hopital's rule, we really need to focus on why, or on when we're using it. It's indeterminate forms. Let me show you on the next slide the proof, and you'll, I hope, see why it has to be an indeterminate form. So L'Hopital's rule again states that if you have a function in this form, that you can take the derivative of the top, derivative of the bottom, and reevaluate the limit, and they have to be the same. So I start with the end, that the derivative of f prime of x over g prime of x as x approaches a. And remember, we had an indeterminate form. So I rewrote those derivatives as slope statements, change in y over change in x. You see I did that with both of them. Okay, so that's just a slope statement. Well, in dividing fractions, you multiply by reciprocals, so what happens is the x minus a's cancel out. And you end up with just this statement. Well, remember, you had an indeterminate form, which meant when you plugged in a, you got 0 over 0. So this is 0, and this is 0. So f of x minus 0 over g of x minus 0 takes us to this. So what we just proved there is that the two limits, as long as it's an indeterminate form, the two limits must be the same. And that indeterminate form becomes so important because if that wasn't true, these terms that I put the red arrow underneath wouldn't zero out. Okay. Now let me just show you one last thing that L'Hopital's rule is kind of nice for, and it's one of the other indeterminate forms. And my recommendation would be to remember your pre-calc rules for finding horizontal asymptotes over doing this because it can get a bit tedious. But let's say you're taking the limit as x goes to infinity. And of course, your pre-calc rules tell you that if the high power's on the top, there's no limit. The high power's on the bottom, the limit's 0. And if the same power's on top and bottom, you make a fraction out of the coefficients. Well, L'Hopital's rule works for the indeterminate form of infinity over infinity. So imagine plugging infinity in here. We would definitely get infinity over infinity. So we take the derivative of the top, the derivative of the bottom, plug in infinity, we would get infinity over infinity again. Derivative again, we get 6 over 12, which reduces to 1/2, which, if you'd used your pre-calc rules, is what you would have gotten right away. So, again, you can do these limits with L'Hopital, but I think it's probably faster, more time effective to remember your pre-calc rules.